So taking this lab, I mean, now that you've collected your data, you should end up with a data table that looks like this. I've got yours. Okay? Those are the big pieces of information that you're going to need. You're going to need the displacement, the distance it travels down the incline, your recorded times, the average time, and then the average time squared. Okay? So once you've collected all your data, you need to fill that out. Now, in order to put together a halfway decent lab, there's a couple things that you need to do. You need to be able to record your uncertainties with each one of those measurements. How uncertain do you think your displacement measurement is? Okay? How uncertain do you think your measurement in your time is? The old-fashioned way of calculating your uncertainty in time is to use reaction time. It's to simply take that button and see how quickly you can tap it. Okay? So one way of doing it. It's not terribly accurate. What we're going to do instead is that we're going to collect all of our time values. We're going to find the one time value out of my distances that has the largest range, the largest uncertainty, if you will. So from, let's imagine that T1 is 2 seconds, 2.01 seconds, and T4 over here is something like 4.34 seconds. Gosh, let's hope not. That'd be terrible. But that may very well have the largest range. Okay? So we're going to take that largest range. We're going to find the range of that. We're going to take this span. We're going to find the difference, if you will, between those 2 points. So we're going to take the 4.34 and we're going to subtract 2.01 from it. Largest. We're going to find the largest spread. We're going to take the range. We're going to take the difference of those two, and then we're going to divide by the average in that time frame, and that will give us our percent uncertainty. Okay? So that percent uncertainty will be associated with all of our time values. This is how much we vary. We vary in our measurements. Cool? And because we're taking 5 time values, our average should be relatively good. Okay? Cool? Now the thing is what about my percent uncertainty and time average squared? Well, it itself has no uncertainty, but it has an uncertainty. I didn't measure time squared, but it does have an uncertainty. So once I've determined the uncertainty of my time squared is just going to be that percent uncertainty plus that percent uncertainty. Because I'm multiplying time times time, I'm adding the percent uncertainties together. So I've calculated the percent uncertainty for time squared. I'm simply going to add those two. So I'm going to take that uncertainty and I'm basically going to multiply it by 2. Okay? So that'll give me my range and my time. My displacement is the same process. We're going to take, the same process that we've done before, I should say. We should take our uncertainty in that measurement, that displacement measurement. Now, it's not a measurement of reaction time. You've made a physical measurement there, and you're trying to measure how much it goes down that track. So that uncertainty is associated with the measuring device. So that should be plus or minus a millimeter. Okay? So you're going to get plus or minus a millimeter divided by that distance, or that displacement. Okay? So you're going to have that plus or minus 1 millimeter divided by 90 centimeters. Obviously, you want your units to match up, but that's basically how you're going to do it. So you're going to have a percent uncertainty for every one of those measurements. And obviously, the 20 is going to have the highest percent uncertainty, and the 90 should have the lowest. Otherwise, you're doing your math. Okay? So once you've filled out this chart, once you've gotten all that done, what you're going to do next is you're going to plot it. And give me a second here while I clean up my board. Okay? So you're going to plot it. You're going to take, okay, here's your axis. You're going to take distance, that did show up, yep, and time squared. You're going to plot that data. Now, we do have computers in our classroom, so if you're not using Excel, then I don't understand what's wrong with you. Okay? I'm not asking you to hand plot it. Just put it in Excel, and we'll plot it that way. It's the easiest way to do it. Now, what you should end up with, if everything goes right, is that you should have a relatively linear fit. Okay? And hopefully it'll go through the origin, but it won't necessarily. And there's a reason for that. Hopefully you have a linear fit, and hopefully it goes through the origin. Now, if it doesn't have a linear fit, then we have a problem. If it doesn't go through the origin, we have a systematic error. No big deal. Okay? So after we plot it, and after we get our linear fit, we can say that that equation of that line is going to be mx plus b. Okay? That equation for that line is going to be mx plus b. Now, what's m, what's x, and what's b? Well, first of all, this is all going to be equal to d, so I'm going to have my displacement is equal to m, my slope, which I don't know yet, which is some numerical value. There's going to be a number in there, and that number is going to have a unit. Okay? If displacement, well, let's finish this discussion first. And then on my x-axis is time squared. So I've got time, and you can be more specific by saying average time squared, but it's time squared plus some other number. Okay? Cool? So that's basically your equation of a line. Now to determine units, well, if this is a meter and this is a second squared, what times second squared is going to give me a meter? Well, that's simple. That's a meter per second squared. The second squared gets canceled out. So if this is a meter per second squared and this is a second squared, those are going to cancel out and I'm left with a meter. Well, the unit that are the physical property that has units of meters per second squared is acceleration. So this would seem to be my acceleration. Okay, now for my intercept value, it's an additive process, so this has got to be a meter plus a meter plus a meter. So that this is going to be a meter. So my intercept, whatever it may be, is going to be a systematic error associated with the distance that I've measured. Okay? It's a systematic error that says, oh, I'm actually have my cart up a little too high, or I have my cart a little too low, or I'm not stopping in time, or whatever it may be. But that's what that is. That's systematic error showing up that way. Okay? Cool? So you have your slope, and it seems to be acceleration. Okay? But it's not. It turns out that your slope here, your m, is going to be 1/2 your acceleration. Now, where that comes from, look at kinematics one dimension. You're not at that point yet, that's fine, but it turns out that when you're taking your derivatives and you're taking your integrals, you end up with an equation that relates displacement to acceleration, and it so happens that displacement is equal to insert velocity initial times time plus 1/2 acceleration times time squared. Okay? So it turns out that that slope is going to be half your acceleration. Okay? So if you want to get your acceleration, you just simply multiply your slope by 2, and that's the acceleration. Cool? Now, next video, I want to take it one step further. You don't have to in this experiment, but if those of you who want to, please do. I mean, it's a pretty interesting thing.